Guglielmo Marconi, born on April 25, 1874, in Bologna, Italy, emerged as one of the most transformative figures in the field of communication technology, credited widely as the pioneer of long-distance radio transmission. From a young age, Marconi demonstrated a curious mind and deep interest in scientific experiments, particularly those involving electromagnetic waves. Though he was not formally enrolled in a university, he studied physics privately and was influenced heavily by the groundbreaking works of scientists like Heinrich Hertz, James Clerk, Maxwell, and Oliver Lodge. His relentless curiosity and passion for wireless telegraphy led him to conduct early experiments at his family estate, where he successfully transmitted wireless signals over short distances, marking the genesis of a revolutionary invention. His early success garnered the Italian government, which, however, dismissed his ideas as impractical. Undeterred, he traveled to England in 1896, where he received a warmer reception. There, he founded the Wireless Telegraph and Signal Company in 1897, which later became known as Marconi's Wireless Telegraph Company. He swiftly obtained a patent for his wireless telegraphy system, which is considered the world's first patent for a radio wave-based communication method. Marconi's work gained significant momentum when he managed to transmit wireless signals across long distances. One of his earliest and most publicized achievements came in 1899 when he sent a wireless signal across the English Channel, bridging the gap between France and England without the need for cables. This accomplishment not only stunned the public, but also signaled the start of a new era in global communication. His fame surged even higher when in December 1901, he achieved the first successful transatlantic wireless transmission, sending the letter S in Morse code from Poldhu, Cornwall, to St. John's, Newfoundland. This monumental feat proved that radio waves could travel beyond the horizon, challenging prevailing scientific beliefs about the limitations of wireless signals. Marconi's achievement was not merely scientific. It carried profound implications for maritime communication and emergency responses, particularly relevant in an era dominated by transoceanic navigation. The success of Marconi's wireless system caught the attention of military and commercial organizations worldwide. His technology was adopted rapidly by naval fleets, and commercial shipping lines began installing Marconi's equipment to improve safety and operational efficiency. Perhaps the most historically impactful instance of Marconi's invention was its critical role in the RMS Titanic disaster in 1912. Though the ship tragically sank, the use of Marconi wireless apparatus aboard enabled distress signals to be sent, leading to the rescue of over 700 passengers. This event solidified the practical importance of radio communication and led to international regulations mandating wireless telegraphy on passenger ships. Marconi, in recognition of his contributions, was awarded the Nobel Prize in Physics in 1909, an honor he shared with German physicist Carl Ferdinand Braun. Their joint recognition underscored the significance of their work in improving wireless telegraphy and laying the groundwork for modern radio. Throughout his career, Marconi remained deeply involved in refining and expanding the capabilities of wireless communication. He explored the use of shorter wavelengths, which allowed for more reliable and efficient transmissions. His experiments contributed to the development of directional antennas, facilitating focused transmissions over greater distances. In the 1920s, Marconi turned his attention to the possibilities of radio broadcasting, conducting successful demonstrations in which speech and music were transmitted wirelessly over considerable distances. These experiments laid the groundwork for what would become modern radio broadcasting, changing the landscape of information and entertainment dissemination forever. His endeavors extended into microwave and radar technologies as well, areas in which he continued to innovate well into the later years of his life. Marconi's legacy also included substantial contributions to international telecommunications policy. As a member of the Italian Senate and a delegate to various global conferences, he advocated for standardized communication protocols and spectrum management. His efforts helped establish a framework for cross-border cooperation in radio frequency regulation, a vital step as more countries began adopting wireless technologies. The scope of his influence extended beyond science and technology, as he was also a prominent figure in Italian society, eventually being appointed president of the Royal Academy of Italy by Benito Mussolini. While this association with fascist Italy remains a controversial aspect of his legacy, it does not diminish the global impact of his technological achievements. Despite his public stature and professional accomplishments, Marconi maintained a relatively private personal life. He married twice and had several children. His devotion to his work never waned, and he continued to lead research projects and represent Italy in various scientific and diplomatic capacities until the final years of his life. He was known for his discipline, charisma, and unwavering belief in the potential of science to improve human connectivity. In the early 1930s, he began experiencing health issues but remained active in scientific circles. He continued to make public demonstrations and deliver lectures that captivated audiences, reinforcing his status as a visionary thinker and innovator. On July 20, 1937, Guglielmo Marconi passed away in Rome at the age of 63, following a series of heart attacks. His death marked the end of a luminous era in the history of communication. The impact of his departure was deeply felt worldwide, with numerous tributes pouring in from scientists, political leaders, and ordinary people who had come to recognize the profound role his inventions played in shaping the modern world. As a mark of respect, radio transmitters around the globe observed a 2-minute silence, symbolizing the breadth of his influence on global communication. His funeral was attended by dignitaries and representatives from various nations, further testament to the international regard in which he was held. Marconi's legacy endures not only in the annals of scientific history, but in every instance where wireless technology enables human connection. His name remains synonymous with the dawn of radio, and his innovations laid the foundation for television, mobile communication, and the vast array of wireless technologies that define contemporary life. Institutions bearing his name, from research centers to schools, continue to honor his contributions to science and society. Though decades have passed since his death, the resonance of his work continues to echo through time, just like the invisible waves he first tamed to send messages across the oceans. Marconi's life stands as a testament to how vision, perseverance, and scientific inquiry can transform the very fabric of civilization. John Logie Baird, born on August 14, 1888, in Helensburgh, Scotland, was a trailblazing inventor whose name became forever linked with the creation of mechanical television, a technology that laid the foundational stones for the modern era of visual broadcasting. Raised in a modest household, he exhibited an early fascination with electricity and mechanical devices, often tinkering with household items and conducting small experiments. His enthusiasm for science was nurtured during his studies at the Royal Technical College in Glasgow and later at the University of Glasgow, though his formal education was cut short due to ill health. Despite his limited academic credentials, Baird's determination and inventive spirit drove him to pursue breakthroughs in communication technology. He embarked on various ventures, some of which included early ideas for synthetic diamonds and a glass razor, but these did not yield financial or technical success. It was his persistent work with the transmission of visual images through mechanical scanning systems that eventually placed him at the forefront of a technological revolution that would change the way humanity experiences information and entertainment. During the early 1920s, Baird began exploring the possibility of transmitting moving images over distance using mechanical systems rather than electronic ones, which were not yet sufficiently developed for this purpose. He focused on using the Nipkow disk, a spinning disk with a spiral pattern of holes, to scan images and convert them into electrical signals. He worked under financially constrained conditions, often using household materials such as bicycle parts, cardboard, and old electric motors to assemble his prototype. In 1924, after much experimentation, he managed to transmit a flickering image of a ventriloquist's dummy, which marked one of the earliest instances of moving pictures being transmitted by mechanical means. Encouraged by this progress, Baird moved to London, where he continued refining his invention. He secured space in Selfridge's department store to conduct a public demonstration, drawing significant public and media attention despite the rudimentary quality of the images. His relentless innovation led to a major milestone in 1926, when he gave the first recognized demonstration of true television before members of the Royal Institution and a reporter from the Times, showcasing live moving images over a wire transmission. Baird's mechanical television system used a combination of scanning disks, amplifiers, and photoelectric cells to convert light into electrical signals and then back into light on the receiving end. Though the images were crude and low in resolution, they represented a profound technological leap. The development drew attention from both scientific communities and government institutions. In 1927, Baird succeeded in transmitting a signal over 438 miles of telephone line between London and Glasgow, demonstrating the potential for television to span great distances. The following year, he made another remarkable breakthrough by transmitting the first transatlantic television signal from London to New York, once again proving the viability of long-distance video communication. That same year, he achieved the first color television transmission using a modified version of his mechanical scanner and filters. These successive innovations earned him a reputation as a fearless inventor. Undeterred by the technological limitations of his time, his efforts catalyzed a race among scientists and engineers globally to further develop the capabilities of television systems. One of Baird's most significant achievements came in 1928, when he introduced the world's first television broadcast, featuring recognizable human faces. He also demonstrated the first televised close-up of a human face, showing that this new medium could be used for storytelling and personal communication. The potential for television to become a mass medium was beginning to take shape. Baird established the Baird Television Development Company, Ltd., which soon became a leader in the field of mechanical television. Through this company, he developed partnerships with the British Broadcasting Corporation (BBC) and began regular experimental broadcasts. In 1930, the BBC adopted Baird's system for its experimental television service, and his technology was used for the first scheduled television programming in 1932. Though the broadcasts were limited in scope and the image quality was far from perfect, they marked a critical stage in television's transition from an experimental novelty to a public utility. While Baird was enjoying growing recognition, his mechanical approach to television was gradually being overshadowed by emerging electronic television systems, which offered higher resolution and better image stability. Pioneers like Philo Farnsworth and Vladimir Swerykin in the United States were developing electronic television technologies based on cathode ray tubes, which eventually proved more scalable and efficient. Despite this shift in the technological landscape, Baird remained dedicated to advancing his own inventions. He continued improving the mechanical systems and even explored hybrid technologies that combined electronic components with his mechanical framework. In 1939, he gave a demonstration of a 600-line high-definition television system, which was remarkably advanced for its time. He also conducted early research into three-dimensional television and large-screen projection, envisioning applications that would not become mainstream for many decades. Though the world eventually moved on from mechanical systems, his groundbreaking work served as the launchpad for those very advancements. Baird's contributions were not confined to the laboratory. He was also a visionary who understood the social implications of visual broadcasting. He imagined a future where people could attend concerts, watch plays, and participate in distant events through television screens in their homes. His predictions, though ambitious for the time, turned out to be astonishingly accurate. The passion he had for bringing people together through shared visual experiences was reflected in his tireless experimentation and forward-thinking ideas. Even as his health began to decline, he remained intellectually active and continued to dream of new frontiers for television. He advocated for international standards in broadcasting and hoped to see television used as an educational tool, capable of bridging cultures and spreading knowledge to even the most remote corners of the globe. John Logie Baird passed away on June 14, 1946, in Bexhill-on-Sea, Sussex, after suffering a stroke. He was 57 years old. His death marked the conclusion of a life that had been wholly dedicated to invention, exploration, and the pursuit of technological progress. Though his mechanical television system was eventually rendered obsolete, his pioneering work had already secured his place in history. He was posthumously honored in various ways, including being inducted into the Scottish Engineering Hall of Fame and receiving recognition from television societies around the world. Museums, educational institutions, and public monuments commemorate his work, ensuring that his legacy is preserved for future generations. The innovations he introduced, and the boldness with which he pursued his vision, paved the way for an industry that now plays an indispensable role in global society. His life stands as a testament to how imagination, persistence, and a relentless pursuit of innovation can shape the course of history and redefine how people connect with one another. Philo Farnsworth, born on August 19, 1906, in a humble log cabin in Beaver, Utah, emerged as one of the most influential inventors of the 20th century, credited with creating the world's first fully functional, all-electronic television system. Growing up in a rural farming environment, He displayed an innate curiosity about how machines worked and demonstrated exceptional intellect from a young age. His interest in electricity was sparked when his family moved to a house with electrical power, where he became fascinated by the appliances and wiring that brought light and energy to everyday life. As a teenager, he consumed scientific literature voraciously and conceptualized the principles of an electronic television long before any prototype had materialized. By the time he was in high school, he had already envisioned how electrons could be used to scan, transmit, and project moving images, laying the groundwork for an invention that would revolutionize global communication. His teacher was so impressed by one of his chalkboard diagrams explaining image scanning that he preserved it as a reference. An early glimpse of Farnsworth's inventive potential. Philo's moment of inspiration came while he was tilling a potato field in Idaho, where the parallel rows of crops helped him conceptualize how images could be scanned, line by line, using an electron beam. This visualization became the foundation for what would later become known as the image dissector, a device that would enable electronic scanning of images for television transmission. By the age of 21, Farnsworth had designed and built a functioning prototype of his electronic television system, including the camera tube and the receiver. He filed for patents in 1927, and soon demonstrated the viability of his invention to investors and scientific observers, transmitting a straight line that could be seen on a cathode ray tube. This breakthrough marked the first time in history that images were successfully transmitted and received using only electronic components, without the need for mechanical parts, such as spinning discs or mirrors, which had limited the performance of earlier attempts by inventors like John Logie Baird. Farnsworth's early success attracted attention from scientific communities, entrepreneurs, and even competitors. One of his major rivals was the Radio Corporation of America, RCA, led by David Sarnoff, which aimed to dominate the rapidly emerging television industry. RCA had invested heavily in Vladimir Zworykin's research, a Russian-born engineer working on a similar concept known as the A contentious legal battle ensued over the patent rights to television technology, with Farnsworth defending his intellectual property against a much larger and more powerful opponent. In a landmark court ruling, Farnsworth emerged victorious. In 1934, with a judge acknowledging that his designs predated Zworykin's and constituted the foundational innovation behind electronic television. This legal triumph granted Farnsworth recognition as the rightful originator of the core technology that made television possible, though the prolonged litigation strained his resources and delayed his commercial aspirations. Despite legal challenges, Farnsworth pressed forward with the development and refinement of his television system. He founded Farnsworth Television and Radio Corporation, which aimed to manufacture electronic television sets and broadcast equipment. In the late 1930s, he established one of the first television production studios, which created original content for demonstration and experimental broadcasts. During World War II, however, the commercial rollout of television was halted as manufacturing shifted to military needs, and Farnsworth factory was repurposed for defense electronics. Nonetheless, he contributed to radar technology and other wartime innovations, continuing to showcase his versatility and engineering prowess. Once the war ended, interest in television surged, and Farnsworth resumed efforts to commercialize his inventions. Although he now faced stiff competition from better-funded corporations that had entered the field during the war years, commitment to innovation extended beyond television. In the post-war era, he delved into atomic energy research, seeking to find peaceful applications for nuclear power. He also explored the development of a device known as the fusor, a type of nuclear fusion reactor that generated interest in scientific circles for its novel approach to producing energy through fusion rather than fission, though it did not result in a practical energy source. His work laid the foundation for future research in fusion science and was recognized as an important conceptual advancement. Farnsworth also investigated early computing technologies and held over 300 patents related to various electronic and scientific systems. His inventiveness was not limited to one domain. Instead, he approached every problem with the same analytical mind that had enabled him to unlock the mysteries of electron-based imaging decades earlier. Despite his achievements, Farnsworth struggled with the commercial exploitation of his inventions. Larger corporations with extensive resources came to dominate the television market, leaving him and his company overshadowed. The stress of continual legal and financial battles took a toll on his health and morale, and he found it increasingly difficult to maintain control over the technologies he had pioneered. His contributions were often underappreciated during his lifetime, as other names became more closely associated with the burgeoning television industry. Yet, among engineers and historians, he remained a revered figure whose work had been instrumental in making modern broadcasting possible. His resilience in the face of adversity and his devotion to scientific integrity earned him admiration and respect among those who understood the magnitude of his impact. Philo's personal life was grounded in the support of his wife, Elma Pem Farnsworth, who worked closely with him throughout his career and remained his steadfast partner during the turbulent periods of litigation and business setbacks. Together they had children and lived modestly, even as the world reaped the benefits of the technology he had conceived. In later years, as television became ubiquitous in homes around the world, he was invited to various ceremonies and honored for his role in its development. One poignant moment occurred during a visit to a television studio, where he witnessed the vast array of programming being broadcast, prompting him to reflect that the technology he had envisioned so long ago had indeed reached its full potential, in ways he had only dreamed of as a young inventor. Philo T. Farnsworth passed away on March 11, 1971, in Salt Lake City, Utah, following years of declining health. Though his death was not marked by widespread public fanfare, his legacy quietly endured in the screens that had become a central fixture in global culture. Over time, his contributions gained broader recognition, and his story was revisited in documentaries, academic research, and even dramatizations that celebrated the underdog inventor who dared to take on corporate giants and win. Today, his name is engraved on monuments and science awards, and his image has appeared on commemorative stamps and in museum exhibits that pay tribute to his genius. His work is considered one of the cornerstones of electronic media, and every pixel that lights up in a television screen bears silent testament to the principles he articulated almost a century ago. Philo Farnsworth's life journey exemplifies the power of vision, persistence, and ethical innovation. His ideas were ahead of their time, and his ability to transform a childhood fascination into a groundbreaking technology underscores the limitless possibilities of the human mind. Though he faced immense obstacles, his determination to see his ideas through altered the course of history and reshaped how people across the globe experience storytelling, news, education, and entertainment. His pioneering invention laid the bedrock for the television industry, which continues to evolve in new and complex ways. The spirit of his work lives on not only in technology, but in the imagination of future inventors who, inspired by his legacy, continue to push the boundaries of what is possible. Hedy Lamarr, born Hedwig Eva Maria Kiesler on November 9, 1914, in Vienna, Austria, is remembered not only for her illustrious career as a Hollywood actress, but also for her remarkable and underappreciated contribution to the world of science and technology through the invention of frequency-hopping spread spectrum. Raised in a cultured Jewish family, she demonstrated an early aptitude for both the performing arts and scientific curiosity. Her father, a bank director with a passion for explaining mechanical devices, often engaged her in technical discussions that fueled her interest in understanding how things worked. While she initially pursued acting and quickly gained fame in Europe for her roles in provocative and emotionally charged films, her intellectual pursuits continued in the background, revealing a mind deeply engaged with innovation and technical problems. As she transitioned to Hollywood and rose to stardom during the golden age of American cinema, starring in numerous films that captivated audiences with her beauty and talent, Lamarr privately maintained a fascination with inventions and mechanical engineering, often setting up a workshop in her home where she would tinker with new ideas between film shoots. Amidst the glitz and glamour of her acting career, Lamarr became increasingly concerned with global events, particularly the rise of fascism and the ongoing devastation of World War II. Drawing on her knowledge of technology and inspired by a desire to help the Allied war effort, she began to think about ways to improve secure communications for military use. Her collaboration with composer and inventor George Antheil proved to be a turning point in her journey from actress to innovator. The two shared a mutual interest in science and developed a concept for a radio guidance system that could use frequency hopping to prevent enemy interception or jamming of signals, controlling torpedoes. By constantly switching the radio signal across a range of frequencies in a synchronized pattern between transmitter and receiver, the system would be difficult to detect or disrupt, enhancing the reliability and security of wireless military communications. The mechanism they proposed was inspired partly by Antheil's work with synchronized player pianos, an analogy that helped them visualize how to coordinate signal hopping in real time using prearranged sequences. In 1942, Lamarr and Ant were granted a U.S. patent for their secret communication system, a pioneering invention that would eventually become the cornerstone of modern spread-spectrum technologies. Although their idea was revolutionary, it was ahead of its time and not immediately adopted by the U.S. Navy, due to limitations in implementing the technology with the existing hardware of the period. Military officials filed away the patent, and Lamarr's contribution went largely unnoticed during her lifetime, overshadowed by her fame in the entertainment industry. Nevertheless, the underlying principles of their system later resurfaced and were incorporated into advancements in wireless communication, particularly in the latter half of the 20th century. Frequency hopping became an essential component in technologies such as Bluetooth, Wi-Fi, and GPS, proving the enduring value of her foresight and ingenuity. The ability of this method to reduce interference, increase bandwidth efficiency, and enhance signal security has made it indispensable in countless civilian and military applications around the globe. Despite the groundbreaking nature of her invention, Lamarr received little recognition during the decades that followed. She continued her film career throughout the 1940s and 1950s, starring in major studio productions and remaining a household name for her acting. But her intellectual achievements remained hidden from public awareness. Throughout her life, she felt a deep sense of disappointment that her contributions to science were overlooked, especially as she watched the rise of technologies that bore the mark of her original ideas. It wasn't until the 1990s that her work in communication technology began to receive the attention it deserved. Scholars and historians revisited the patent she authored, and telecommunications experts acknowledged the foundational nature of her invention. As a result, she began to be celebrated not just as a screen legend, but also as a visionary inventor, whose contributions had a far-reaching impact beyond the film industry. Recognition came in the form of various awards and honors that helped solidify her place in scientific history. In 1997, she was awarded the Electronic Frontier Foundation's Pioneer Award, which acknowledged her and Antio's contribution to modern digital communication systems. That same year, she was also the first woman to receive the Bobby Nass Spirit of Achievement Award, an honor typically reserved for lifetime inventors. Though Lamarr had long retreated from the public eye and lived in relative seclusion, these acknowledgements gave her a renewed legacy as more than just a glamorous figure of classic cinema. Her story gained broader public attention through documentaries, books, and articles that aimed to correct the historical oversight and shine a light on the extraordinary duality of her life. She became an inspiring figure for women in science and technology, illustrating that brilliance and creativity can flourish in any context, and that one's appearance need not define the boundaries of their intellect. Lamarr's life was marked by both personal triumphs and challenges. She was married 6 times and had 3 children, often navigating the complexities of fame, relationships, and the pressures of a career in a male-dominated industry. Despite these hurdles, she maintained her inventive spirit, continuing to sketch designs for various devices well into her later years. Her interests ranged from improving traffic signals to creating dissolvable tablets that could flavor drinks, showing the breadth of her imagination. Though not all of her ideas were commercialized or brought to fruition, they revealed a persistent and inquisitive mind that sought to solve problems creatively. Her blend of artistic and scientific pursuits set her apart as a unique figure in the annals of history, defying the simplistic categorization often imposed on public figures. On January 19, 2000, Hedy Lamarr passed away in Castleberry, Florida, at the age of 85. In accordance with her wishes, her ashes were scattered in the Vienna woods, a symbolic return to the place where her life began. Her passing marked the end of a journey that traversed the worlds of art, science, war, and innovation. Only in retrospect has the full scope of her contributions been truly appreciated. As more people come to understand the depth and complexity of her achievements, today, her legacy lives on, not only through the films that continue to enchant audiences, but also through the invisible infrastructure of modern communication networks that trace their origins back to her inventive mind. Her life is a powerful reminder of the importance of recognizing talent in all its forms, and ensuring that creativity, no matter where it appears, is given the opportunity to flourish. Hedy Lamarr's story serves as an enduring example of how unconventional paths can lead to extraordinary outcomes. Her work in frequency hopping spread spectrum was not the product of formal engineering training, but rather the fruit of insight, collaboration, and an unyielding curiosity about the world. By daring to think differently and acting upon her ideas, in a time when women were seldom acknowledged in technical fields, she shattered barriers and redefined what was possible. Her dual legacy as a cinematic icon and a technological pioneer continues to inspire new generations to pursue their passions boldly, regardless of societal expectations. Through her contributions, she changed both the art of storytelling and the science of connectivity, leaving behind a world more united, informed, and empowered than she found it. Eli Whitney, born on December 8, 1765, in Westborough, Massachusetts, played a pivotal role in shaping the course of American history through his groundbreaking invention of the cotton gin, a device that would drastically transform agricultural practices and industrial growth in the United States. Raised in a modest New England household, Whitney exhibited an early affinity for mechanics and engineering, crafting violin parts and other intricate items during his youth. His resourcefulness and intellectual curiosity led him to Yale College, where he graduated in 1792, gaining a formal education that complemented his natural talent for invention. Following his academic pursuits, he traveled south to Georgia in hopes of securing a position as a private tutor. While residing at the plantation of Catherine Greene, the widow of Revolutionary War General Nathaniel Greene, he became aware of a pressing issue that plagued Southern cotton farmers. The prevalent strain of cotton, known as short staple cotton, grew prolifically in inland areas, but was incredibly labor-intensive to process due to its tightly embedded seeds. Manually separating seeds from cotton fibers consumed hours of effort for just a small yield, limiting productivity and profitability. Whitney, motivated by both his inventive spirit and the challenge at hand, set out to develop a mechanism that would streamline the cotton cleaning process. Drawing on his mechanical insight and improvising with basic materials such as wire, wood, and nails, he designed a machine in 1793 capable of efficiently extracting seeds from cotton bolls. The device used a series of rotating brushes and metal teeth to pull cotton through a mesh that trapped the seeds while allowing clean fibers to pass through. This simple yet effective contraption revolutionized cotton processing by reducing the time required to clean a pound of cotton from many hours to mere minutes. With the cotton gin, productivity soared, and cotton rapidly became a dominant crop in the Southern economy. Whitney partnered with entrepreneur Phineas Miller to patent and promote the invention, receiving a patent in 1794. Despite this legal protection, widespread infringement and unauthorized duplication of the cotton gin severely hampered their ability to profit from the invention, leading to numerous legal battles that drained resources and yielded limited compensation. Although the cotton gin was designed to alleviate manual labor, its widespread adoption had profound and complex consequences. By making cotton cultivation vastly more efficient and lucrative, the device inadvertently strengthened the economic foundation of plantation agriculture. This in turn escalated the demand for enslaved labor to plant, harvest, and process increasingly vast fields of cotton. Southern planters, recognizing the profitability of the new system, expanded their operations, fueling the entrenchment of slavery in the American South. Whitney had not anticipated this outcome, and the unintended societal impact of his invention became a central paradox of his legacy. While the cotton gin represented a triumph of ingenuity, it also contributed to deepening divisions that would later culminate in national conflict. Nonetheless, the device's technological importance is indisputable, as it laid the groundwork for America's emergence as a global cotton supplier and a key player in the burgeoning textile industry during the Industrial Revolution. Beyond his contributions to agriculture, Whitney left a lasting mark on manufacturing and industrial organization. In the late 1790s, he secured a government contract to produce 10,000 muskets for the U.S. Army, at a time when most firearms were crafted individually by skilled artisans. Embracing the concept of interchangeable parts, Whitney sought to standardize production so that components could be mass-produced and assembled with minimal hand-fitting. Though initial progress was slow and his methods faced skepticism, Whitney eventually demonstrated the practicality of this system, showcasing a set of musket parts that could be swapped and reassembled seamlessly. This demonstration, though likely staged to some extent, symbolized a shift toward modern industrial practices and signaled the birth of standardized mass production in America. The principles Whitney advocated would later be embraced fully in the American system of manufacturing, forming the basis of factory efficiency, assembly lines, and large-scale production that defined the industrial age. Despite the revolutionary nature of his work, Whitney faced numerous obstacles throughout his career. The legal struggles over the cotton gin patent consumed years and financial resources, and his manufacturing efforts were hampered by supply challenges and technical hurdles. Yet his resilience and innovative thinking enabled him to adapt and persevere in the face of adversity. He remained deeply involved in his arms manufacturing business, which prospered and expanded after his death. Whitney's later life was marked by recognition and respect within scientific and industrial circles, and his influence extended to future inventors and entrepreneurs who built on his concepts. He continued to refine his methods, seeking efficiency and reliability in production processes, which reflected his commitment to progress and improvement. Eli Whitney passed away on January 8, 1825, in New Haven, Connecticut, succumbing to prostate cancer at the age of 59. His passing marked the conclusion of a life that bridged the agrarian traditions of the early United States and the mechanized transformations that would define its industrial future. Though many of the innovations he championed took years to be fully realized, their enduring impact on technology, economics, and labor systems solidified his role as a foundational figure in American innovation. In the years following his death, institutions, towns, and educational programs would come to bear his name, honoring the visionary who fundamentally altered how goods were produced and processed. The dual legacies of his work, one highlighting technological advancement and the other reflecting the darker social ramifications of progressive, a nuanced and thought-provoking portrait of innovation's power to shape both opportunity and consequence. The cotton gin remains one of history's most iconic inventions, not solely because of its mechanical simplicity, but because of the vast ripple effect it had on global trade, labor patterns, and industrial development. Whitney's ability to identify a critical problem, devise an elegant solution, and pursue its implementation speaks to the enduring nature of human creativity and perseverance. His vision extended beyond immediate profit or fame. He aspired to improve the efficiency of systems and to make labor more productive. In doing so, he contributed to the economic rise of a nation and established principles of production that would echo through centuries. Though he could not foresee every outcome of his inventions, Whitney's legacy remains embedded in the fabric of American history, as both a testament to genius and a reminder of the profound influence innovation can exert on society. Samuel Morse. Samuel Morse, born on April 27, 1791, in Charlestown, Massachusetts, was a man of diverse talents, whose most enduring contribution to the world came through his invention of the telegraph and the development of Morse code, a communication system that revolutionized long-distance messaging. Raised in a household where learning and culture were emphasized, Morse was exposed to both intellectual rigor and artistic appreciation from an early age. His father, a preacher and geographer, encouraged him to pursue education, which led Morse to attend Phillips Academy in Andover and later Yale College. While at Yale, he studied various subjects including religious philosophy, mathematics, and science, developing a keen interest in electricity and its potential applications. Though he initially pursued a career as a portrait painter and gained considerable recognition in artistic circles, his lifelong fascination with science remained alive in his mind, laying the foundation for an extraordinary shift in his professional focus later in life. His travels to Europe further honed his skills in fine art, but he was also exposed to emerging technological ideas that would shape his future path. The turning point in Morse's life occurred during a sea voyage from Europe back to the United States in 1832, where a conversation about electromagnetism planted the seed for a transformative idea. Inspired by the possibility of using electrical impulses to convey messages, he began conceptualizing a system that could transmit information over wires. This idea grew rapidly, and Morse dedicated himself to developing a practical solution that could bring this vision to life. With limited formal training in engineering, he relied on his intellect and perseverance, gradually building experimental models and refining his concept. He received critical assistance from collaborators such as Leonard Gale, a professor of science, and Alfred Vail, a skilled machinist and inventor who helped design and improve the working parts of the telegraph system. Together, they overcame many technical challenges and devised a functioning prototype capable of sending electrical signals across a length of wire, demonstrating the feasibility of instantaneous long-distance communication using electromagnetic principles. Morse's key innovation was not just the mechanical device, but also the creation of a language to encode information. He developed a system of dots and dashes, representing letters and numbers, that could be sent as electrical pulses. This symbolic alphabet became known as Morse code, a structured and efficient way to encode complex messages into simple binary signals. The code's simplicity allowed for rapid learning and accurate transmission, making it ideal for operators to use in hypershare environments. In 1837, Morse applied for a patent and continued refining the telegraph's functionality while seeking financial and political support to expand its use. Despite initial skepticism and bureaucratic resistance, his relentless advocacy eventually secured government interest. In 1843, Congress appropriated funds for an experimental telegraph line between Washington, D.C., and Baltimore, marking a pivotal moment in the invention's history. The first message sent over the completed line in 1844, "What hath God wrought," was received with awe and heralded the dawn of a new communication era. The success of that demonstration established Morse as a technological pioneer and opened the door for widespread telegraphy. As the system spread across the United States and into Europe, Morse's invention dramatically changed the way information traveled. News that once took days or weeks to deliver could now be transmitted in seconds, fundamentally altering commerce, journalism, diplomacy, and personal correspondence. The telegraph became the backbone of 19th-century communication infrastructure, enabling faster decision-making, improved coordination of transportation systems, and the expansion of financial markets. Railroads adopted the technology to synchronize schedules, while news agencies used it to dispatch stories almost instantly. Governments leveraged its capabilities for diplomatic messaging and military operations, reshaping international relations and national security strategies. Morse's vision of a connected world, enabled by electrical signals and standardized coding, became a reality far beyond the scope of his original aspirations. As telegraph networks expanded globally, Morse's name became synonymous with innovation and progress. He was honored with awards and recognition from various international institutions, receiving medals and honorary degrees for his contributions. Despite his scientific accomplishments, Morse also faced legal battles and patent disputes. Over the invention's originality and ownership, competitors challenged his rights, leading to court cases that ultimately affirmed his role as the primary inventor of the telegraph system. These disputes underscored the growing importance of intellectual property in the rapidly evolving industrial landscape. Through persistence and the support of his colleagues, Morse retained the credit he deserved, although the financial rewards were not always proportional to the global impact of his work. His legacy, however, continued to grow. As nations built their communication systems using the principles he had pioneered beyond the realm of invention, Morse maintained strong views on social and political issues, engaging in public debates and expressing opinions that sometimes provoked controversy. Nonetheless, his contributions to science and communication remained central to his identity and historical reputation. Even in his later years, he continued to promote technological advancement and took pride in the knowledge that his work had bridged great distances, connected communities, and brought people closer together. His invention anticipated many of the core principles of modern communication networks, including signal encoding, transmission protocols, and relay systems. These ideas laid the groundwork for subsequent innovations, such as the telephone, radio, and ultimately the Internet, each building upon the foundational structure established by the telegraph and Morse code. Samuel Morse passed away on April 2, 1872, in New York City at the age of 80. His death marked the end of a life that had transitioned from artistry to scientific invention, leaving behind a legacy that combined technical ingenuity with a vision of global connectivity. Monuments and memorials were erected in his honor, including statues in major cities and commemorative ceremonies that paid tribute to his influence on communication history. Institutions and schools bear his name, preserving his contributions for future generations to study and appreciate. The simplicity and effectiveness of Morse code allowed it to remain in use for over a century, even surviving well into the digital age as a fallback or specialized signaling method in aviation, maritime, and military operations. His name, etched into the fabric of history, represents not only a particular device, but also a fundamental change in how people exchange information. Morse's life serves as a testament to the power of interdisciplinary talent, combining art, science, and determination to achieve lasting innovation. His journey from painting portraits to crafting electrical messages exemplifies how curiosity and adaptability can lead to world-changing ideas. While his achievements were rooted in a specific technological era, their relevance continues to echo through the infrastructures that define modern life. The lines of code and pulses of electricity that now transmit data across fiber optic cables and wireless networks all trace their lineage back to Morse's original insight that information could be translated into signals and sent across great distances. In recognizing his role in this transformation, the world acknowledges a man whose intellect, perseverance, and vision helped shrink the world and usher in a new age of connection. Through his efforts, the silent spaces between cities and continents were bridged, paving the way for the information age and forever altering the rhythm of human communication. George Westinghouse. George Westinghouse, born on October 6, 1846, in Central Bridge, New York, was a prolific inventor and visionary industrialist who played a central role in shaping the modern world. Through his development and promotion of alternating current AC power systems alongside Nikola Tesla, raised in a mechanically inclined household, he demonstrated an early fascination with engineering and innovation, often spending his time dismantling and studying machines. His father owned a machine shop, where young George gained valuable hands-on experience that would become the foundation of his inventive career. When the American Civil War broke out, Westinghouse briefly served in the Union Army and later joined the Navy, where he encountered steam and mechanical systems firsthand, deepening his interest in technological advancement. After the war, he returned to civilian life and began developing practical inventions, quickly distinguishing himself with ideas that addressed real-world challenges. One of his earliest successes was the invention of a rotary steam engine, which led to several more innovations, including the railroad air brake that significantly improved train safety and efficiency. As the industrial landscape evolved and demand for electrical power increased, Westinghouse turned his attention to electricity, recognizing its transformative potential for cities, industries, and households. At the time, the dominant model for power distribution was the direct current DC system championed by Thomas Edison. While DC had certain advantages, it was limited by its inability to transmit electricity efficiently over long distances. Westinghouse identified this limitation and began investigating alternatives that could overcome the drawbacks of direct current. His research led him to alternating current, a system that could be transmitted over far greater distances with minimal energy loss, making it more suitable for widespread adoption. In 1886, he founded the Westinghouse Electric Company and began acquiring patents and developing equipment necessary for AC power generation and distribution. His interest in AC deepened when he learned about the work of Nikola Tesla, a brilliant inventor who had developed a practical design for the AC induction motor and related components, essential for a viable alternating current infrastructure. Recognizing the significance of Tesla's ideas, Westinghouse purchased the rights to his patents and brought him on board, forming a partnership that would challenge the dominance of Edison's DC empire. Together, Westinghouse and Tesla began building the components of an AC system, including transformers, generators, and motors, all of which were integral to efficient electrical distribution. Their collaboration led to a technological revolution that fundamentally altered how energy was delivered and consumed. The introduction of transformers allowed voltage to be increased for transmission and decreased for safe usage in homes and businesses, solving a major obstacle in long-distance power distribution. Despite the elegance of the AC system, it faced fierce opposition from Edison and his supporters, who launched a campaign to portray alternating current as dangerous and unsuitable for public use. Known as the War of Currents, this rivalry saw both sides compete aggressively for contracts, influence, and public support. Westinghouse maintained his commitment to AC despite the challenges. Driven by his belief in its superiority and long-term potential, his strategic business acumen and engineering insight allowed him to navigate the technical and political obstacles that arose during this contentious period. In 1893, Westinghouse achieved a major victory when his company was awarded the contract to power the world's Columbian Exposition in Chicago. This event served as a high-profile demonstration of AC power's effectiveness, reliability, and scalability, stunning audiences and validating the alternating current model on a global stage. Following this success, Westinghouse secured another landmark achievement by winning the contract to build the hydroelectric power plant at Niagara Falls, a project that showcased the ability of AC power to harness natural energy sources and deliver electricity over vast distances. The successful completion of this project marked the beginning of large-scale electrification, and established AC as the standard for electrical distribution in the United States and beyond. Through his relentless pursuit of innovation, Westinghouse not only revolutionized power systems but also transformed modern industry. He founded numerous companies, employed thousands of workers, and held more than 300 patents over the course of his career. His interests extended beyond electricity to include natural gas distribution, railroads, and industrial manufacturing, each area benefiting from his inventive mind and dedication to practical engineering solutions. Unlike many of his contemporaries, Westinghouse believed in fair labor practices and was known for treating his employees with respect, offering better working conditions and shorter hours than most industrialists of his time. His progressive views on labor and management earned him admiration and loyalty, helping him build a strong and sustainable business empire. He also invested in research and development, supporting scientists and engineers in their work and fostering an environment of creativity and problem-solving that kept his companies at the forefront of innovation. Despite his successes, Westinghouse encountered financial difficulties later in life, as economic downturns and competitive pressures strained his businesses. By the early 1900s, he lost control of his primary company due to a boardroom coup, though he continued to influence the engineering world through advisory roles and smaller ventures. He remained committed to technological progress and continued supporting advancements in transportation and energy. His health began to decline in his later years, yet he stayed engaged with developments in science and remained a respected figure in industrial and scientific circles. His contributions to the modernization of infrastructure and the global adoption of AC power left an indelible mark on history, reshaping cities, industries, and daily life for millions of people. His work laid the foundation for the electrical grid as it exists today, with his vision and perseverance ensuring that energy could be accessed more widely, efficiently, and affordably than ever before. George Westinghouse died on March 12, 1914, in New York City at the age of 67. Due to his service in the Civil War, he was buried in Arlington National Cemetery, a recognition of his dedication to both his country and the cause of progress. In the years following his death, his legacy was celebrated through memorials, museum exhibits, and educational institutions that honored his role in electrifying the modern world. Though often overshadowed by more flamboyant figures like Edison or Tesla, Westinghouse's steady leadership, technical insight, and ethical approach to business established him as one of the most important and underrated figures of the industrial age. His ability to translate visionary concepts into tangible systems that improved lives across the globe reflects the essence of true innovation. The systems he championed continue to power cities, drive economies, and connect communities, affirming the enduring value of his contributions. Through his collaboration with Tesla and unwavering support for AC power, he enabled a new era of technological possibility and set in motion changes that would ripple through every aspect of modern civilization. His story exemplifies how perseverance, intellect, and a commitment to public benefit can overcome adversity and create a lasting impact that spans generations.